Hi everybody, it's Anwar here. This is the recording of the session 4 GC surgery, part 2 on the GC uncertainty. Here we go. So in the first part of the session 4, we have been talking about how to get the uncertainty of individual component by looking at the two standard deviation of the calibration result by converting the calibration result into a normalized component. The next thing that we're going to need to do is how do we convert this individual uncertainty values from each component into a calculation standard uncertainty such as CV uncertainty, line density uncertainty, and it's all dependent on the calculation standard that we have. So I'm going to talk about mainly about ISO 6976 calculation on the CV, but the same exact principle can be applied to any other calculation that have gas composition as their input. So to begin with, let's say we have a calibration gas, and let's say this particular calibration gas that I have has this particular uncertainty here. We got a relative uncertainty of that particular calibration gas. All of the components have plus minus around 2% uncertainty apart from methane, which is less than everything else, plus minus 0.17%. So what does it mean? How do we convert this into uncertainty of CV? So the best way to do an uncertainty calculation is by simulator using a Monte Carlo method. What Monte Carlo method does is basically we simulate all the possibilities of the number that falls in within a certain range and enter those input into the calculation and see the outputs. So if we put enough data in there, we have enough variation in the output, and then we can tell based on the variation of the output the actual uncertainty of the calculation itself. So to show you the Monte Carlo method on the particular uncertainty calculation that we're doing, I'm going to start with this methane uncertainty. So let's say we have a methane component that has concentration of 84.9977. And in our particular example, it has an uncertainty of plus minus 0.15. So what happened here is that if you see these individual components here, this is where the methane component can fall in. It's basically within this range and sometimes can actually go out with this range slightly. So this particular limit here is basically our 95% confident that the value falls within this particular limit. So what we're doing with the Monte Carlo is we generate all these random numbers on methane and everything else. And what we did was we generate 100,000 data with all the possibilities of that particular range. So if we see this particular chart, we basically put the dots on every single methane in there, and it's basically trended on the x-axis as the CV. So we can actually see that we have 100,000 data of methane, and the distribution that we have is basically a normal distribution. So you can see that the average, which is 84.9977, have pretty much the biggest number of number generation, and as we move away from the average, we got lower number of data in there. So what we do then, we basically put every other data in there. So we have methane, 100,000 data. And then we generate ethane, another 100,000 data. And as you see, the distribution is very, very similar to methane. Now this two standard deviation here is taken from the actual uncertainty that we see on that individual component. So we generate the number with this two standard deviation in there. And the distribution is normal distribution. So we generate this number for every single gas. We got 100,000 data for every single gas, and we basically put a combination on all this input and calculate the output. When we see the output, with all this combination of result, we can see the output is pretty much a Gaussian distribution as well. So we got pretty much a big number of data where is pretty much the average. If we use the average gas composition, then we will have the CV of around 38.677 megajoules per standard meter cube. But then from here we can actually see what kind of a standard deviation we have in the CV measurement. In this particular case, we got 0.0558 megajoules per standard meter cube, or 0.1444%. So what this means is that if we take this particular composition with this relative uncertainty, we would expect that the CV measurement will fall in within plus minus 0.1444%. So now we know that this is actually the expected uncertainty from this particular distribution of numbers. Now what we want to do is we want to do another method. The reason why we want to do another method is because when we do a Monte Carlo have a limitation where it requires large numbers of data sets. Large numbers of data sets means it will take a long time to run it before we get a result. So in this particular case, we generated 100,000 data sets and we run it. It took me pretty close to 24 hours to get the result. So what we want to do is we want to look for another method that will be done much quicker. The way to do it is by looking for sensitivity of input towards the output using partial derivative method. So if we do have a computer, we can actually use a numerical method that will come out with a very similar result. Now, to prove that the method is correct, we can then compare the result of our method against the Monte Carlo to prove that our method is actually correct. So what I'm going to show you here is basically what we call GCAS method, and GCAS is basically our software tool to analyze the GC performance. So now I'm going to try to explain what the GCAS numerical method is all about. So let's say this is the gas composition that we have just now. So what we're doing is we take the average value of the calculation of the ISO 6976, and the average value of the gas that we have just now is that particular composition. Now, when we have this mole composition, then we do a calculation of the ISO 6976, and then we get a calorific value of 38.6778. What we do next is we increase the methane component by 0.1%. So in this case, from 84.997, we increase it to 85.082. So while we do that, we basically make sure that every other component here is unchanged. We basically fix the value. So what we tend to see from doing that, we tend to see that the unnormalized total has increased. And then we did another calculation. So we then see the change in the CV. This change we then record it. And then the next thing that we do is we decrease the methane component by 0.1%. So in this case, from 84.997 to 84.912, while the rest of the components are still fixed. And then from there, we record the value of the CEV. So after that, what we get is the impact of the output in comparison against the impact of the input. So if we compare the impact of the output to the impact of the input, what we get is the sensitivity. So the way we do it is basically we get the value of the Y impact, or the output of the impact, which is basically the first value of the output when methane is increased, and then the second value of the output when the methane is decreased, and divide that by the average, and that's what we get as a Y impact. And after that, we got the X impact, or the input impact. So basically, again, the increased value minus the decreased value divided by the average, and we basically get the input impact. So sensitivity then is the output impact divided by the input impact. And what we get here is 0.019. What this means is basically we're saying that for every percent change of methane, CV will change by 0.019%. So, and that's what we basically call as sensitivity. So we did this for methane, and then we have to do it for all other components. What we then see is the sensitivity for every single component. In this particular table, you can see the sensitivity of every single component in this column. So you see methane sensitivity is 0.019, nitrogen is 0.05. So each individual component have a different kind of sensitivity towards the CV measurement. What we then do next is we calculate the standard uncertainty of the CV itself contributed by each individual component. So the standard uncertainty is then the uncertainty of the actual gas multiplied by the sensitivity. Now normally this uncertainty of the calibration gas, we'll be able to get it from the calibration gas certificate. But let's say if we talk about uncertainty of reproducibility from our calibration, then we get it from the 2 standard deviation of it. So we got the uncertainty of the calibration gas in this instance, in this example, and then multiply that by the sensitivity. And what we get is the standard uncertainty. So after that, we can then combine the standard uncertainty of each individual component. And the combined standard uncertainty is basically root sum square of all individual standard uncertainty. So what we do here, the standard uncertainty, we combine them all, and we basically take individual uncertainty of the calibration gas, and then we take individual sensitivity of each individual component, and then root sum square it. And then the root sum square we get is basically the combined standard uncertainty of that particular calibration gas. Now, when we see this, we basically have K equal 1. So K equal 1 means the confidence level of 66%. Why we are using K equal 1? When we do a standard, when we combine uncertainty of everything, we want we want to use the standard deviation rather than 2 standard deviation. Once we get the result, then we can multiply the value by 2, which is the expanded uncertainty. So by multiplying it by 2, we will get a confidence level of 95%. So, and what we get from here is the expanded uncertainty with a confidence level of 95%. In this particular case, we see the result is 0.1458%. So this same exact method can be applied for any other standard, any other calculation even in the ISO 6976 standard itself, such as the standard density, or we can apply this method to the AGA 8 method, and therefore we can calculate the uncertainty of every single calculation result from any calculation standard. So what we do next is we then need to compare it against the Monte Carlo result. So when we see the Monte Carlo uncertainty result, if we remember the result was 0.1444%, and in comparison to the GCAS uncertainty result, we got 0.1458%. So we have a difference of 0.0014. This is considered to be a comparable result to the Monte Carlo result, and it's basically proof that the method is acceptable. Now we do have a slight difference in there, and the difference might be due to the fact that every single gas composition is correlated in there, but because of the difference is so low, it doesn't really matter. It shows that the result is acceptable. So what do we do next? I mean, we now have the capability of calculating the uncertainty value of the GEC. So uncertainty of the GEC is impacted by 4 different parameters. We got uncertainty of the calibration gas, we got uncertainty of the reproducibility, which happens from our daily calibration, and we got uncertainty of the calculation standard, and also uncertainty of the nonlinearity of the thermal conductivity detector. Now, among all these uncertainty inputs, uncertainty from reproducibility or daily calibration is the only thing that will change on a daily basis. So on the daily basis, we get the data from the calibration result. When we record it, we can then calculate the uncertainty of the GC on the daily basis. We call it a life uncertainty, basically. So this is a patented method that we have, which helps a lot in monitoring the performance of the GC. So what we do is basically we grab all the daily calibration data, we record it, and then we trend the uncertainty. Now, there are two ways of calculating the uncertainty. The first one is the forward direction, and the second one is backward direction. Now, this is a little simulation on the forward direction. So basically, as we go along, let's say we have uncertainty that starts somewhere in July there. So every single data is then used to calculate the uncertainty. So all the calibration records that happens from July all the way to the latest calibration result, we combine them all and calculate the uncertainty. So this particular uncertainty, as you see here, we now use like all this data to actually calculate the uncertainty of that particular type. Now, the limitation of the forward direction is when we have a good healthy GC for a long time. Let's say, for argument's sake, we have a GC that has been running very well for the last 1 year, and we, let's say, have a daily calibration in there. What will happen is that, let's say after a year, we have the GC started drifting. So uncertainty values, because we have all this 365 worth of data that is good, 1 day of bad value can be seen as an outlier, so it doesn't really impact the overall uncertainty calculation by too much. So the reaction from the uncertainty calculation result with a forward direction may not be as fast. So what we do next is we introduce the uncertainty looking at backward direction. So what we're doing here, we just basically take the last few data to calculate it as our uncertainty parameters. The default in the software, basically we use the last 30 days or the last 30 data. So therefore, we only get the last 30 data. If there is something gonna go wrong in the GC, the uncertainty data will catch that issue before the issue actually happens. So any single drift that happened in there will be detected as an increment in the uncertainty. So the simulation on the backward direction will look like this. So let's say we have, in this particular example, let's say we have 5 data or 5 days here. So we will only take the last 5 days worth of data, and we will just use those particular period data as our uncertainty calculation. So therefore, if something gonna happen, if there is any drift, like on the 6th data or 7th data in this particular example, then we'll be able to identify that there is an issue with the GC. Of course, 5 data is not right. This is just a simulation. We would suggest to have minimum of 30 data to analyze the performance of the GC. So when we look into the actual case of the GC measurement, this particular trend is coming from a perfectly healthy GC. So this GC, we have been monitoring this for almost a year now, and you can actually see that the uncertainty is really low. 0.1% uncertainty is actually the uncertainty of the calculation standard itself, which is the ISO 6976. So the actual uncertainty that comes from reproducibility of the GC is really low. Now, there is, as you see, there's 2 charts in there. So the light blue one is the forward direction, and the dark blue is backward direction. As you can see, the light blue, which is the forward direction, is a lot more stable, and that's because it's using a lot more data from the system, while the blue one, because it's only using data from the last 30 days, it's a little bit more erratic. But it's not overly erratic. It is something that we do expect from the GC because it's just a natural variation of the response factor of the GC. So if we actually take a look closer of it, it actually looks like that. And as you see, the scale is really, really low. It's only 0.102% of uncertainty of the GC. So from here, we can conclude that the GC is actually working very, very well in a very reproducible manner. I would like to show you that this method can actually identify an issue before we actually have an issue in the GC. So in this particular case, we have a GC that has been working very, very healthily for a while. And as you can see, from this particular point, we start seeing a drift in the uncertainty. So what happened here? We got a drift in the response factor basically, and the response factor drift goes really slowly that normal day-to-day calibration will not be able to detect this. And also when we do repeatability tests, for instance, repeatability tests will always pass. So when we detected that there might be something wrong with the GC when it hits this alarm point, the conventional method of analyzing GC doesn't detect anything. What happened here, we know that the GC is going to fail soon, but what we didn't know that the GC actually failed 2 months after the issue was first detected. So for the last 2 months, we know that the GC is going to fail, but it was still working quite accurately. Only we know that it's going to fail at some point. This allows us to actually order some spare parts, get ready. So if we do have spare parts already, we can identify the issue, identify what might be wrong with it, and actually do something about it before it actually failed completely. So it's a very, very powerful method to look into the actual performance of the GC. Now, if we do not have this method, if we don't identify that there is a problem with the GC, the best thing that we can get out of this method is we can actually know and understand what is the actual performance of the GC, because this also can be used in terms of looking at the actual uncertainty of the GC. Now, when we talk about uncertainty budget, a lot of times people use 0.3% of CV uncertainty in their uncertainty budget of their GC. Now, when you see this particular data, you can actually tell that GC can actually perform so much better than what we thought it can do using the uncertainty budget that we normally use. And the reason why we have this uncertainty budget of such a high tolerance is because the standards that we have at the moment, I think it's probably because of the lack of technology that we had earlier, is identifying a tolerance that is very, very wide. For instance, the ASTM D1945 standard give a tolerance for methane of plus minus 0.1%. Now, methane is, GC measurement of methane is capable of so much better than plus minus 0.1%. So therefore, we can actually understand the actual uncertainty of the GC by using this method rather than assuming quite a high uncertainty of the GC. So this is actually showing the two trends between the overall data and the last 30 days data. You can see the last 30 days data actually reacts a lot faster, which is the dark blue one, and the light blue one is the overall data that we have from there, but it's still giving us pretty much the same similar trend, and this is because we don't have too much of the data prior the GC failure. So when we then see the overall uncertainty, it can then be combined from the calibration gas uncertainty, and we basically put them all in this particular table, and then we get the uncertainty from the reproducibility, which is the daily calibration. Now, this uncertainty, these two uncertainty will have the same similar sensitivity because it uses the same exact component or composition. We then have the calculation standard uncertainty, which comes from the uncertainty standard itself. Normally, when we have a look at the standard, it will identify that this particular standard will have a measurement uncertainty of a certain value. So ISO 6976 have an uncertainty of 0.1%. As you can see here, it shows 0.05% because it is a standard uncertainty, which confidence level of 66%. So expanded uncertainty will be 0.1% basically. So the other thing that we have is the repeatability and linearity uncertainty. Now this comes from the ISO 10723. This sensitivity, we got two different tables of the sensitivity. Now the reason why this is the same is because we pretty much use the same exact component for the range, and that's why the sensitivity is the same, because it's using the same exact component. But in actual case, the calibration gas component may be different from the components of the actual pipeline. Now, when we do the uncertainty of the linearity, we operate on the actual operational range of the pipeline gas rather than the calibration gas, and that's why we have two different sensitivity in there. And this sensitivity is really important as well, which I forgot to mention earlier, in the sense that sometimes we see a certain component will have quite a high uncertainty. For instance, we'll have uncertainty of the calibration gas of hexane here, let's say 0.5%. Now, this doesn't really matter because the sensitivity of it is really low. So that means when you multiply the actual uncertainty of that particular component towards the sensitivity, then the overall uncertainty will become quite low. We had a case of neopentane that have uncertainty of 300%, and the only reason why it has 300% of variation in there is because the neopentane was the neopentane component was 20 ppm. So it's a very, very low component, and therefore it gives a very, very low sensitivity towards the measurement, and it doesn't really impact the uncertainty at all. So I'm not going to talk about the repeatability and linearity uncertainty here. If you are interested about the how to calculate the uncertainty from repeatability and linearity, you can actually open up the ISO 10723 and ISO 6974 standard. It explains it, how to calculate the uncertainty from the non-linearity and repeatability in there. On the next session, I'm going to talk about the ISO 10723 multi-level calibration, and mainly I'm going to talk about the bias and the impact of the bias rather than the uncertainty aspect of it. So that's basically my GC surgery. If you do have any question, we will be able to answer your question. You'll be able to post your question in our GC surgery group in LinkedIn. If you are in LinkedIn and want to join in the GC surgery group, please search for gas chromatograph in the bracket GC surgery, or you can just search for GC surgery. It will come with our group in there. And this presentation also will be made available in the GC surgery group, or if you're watching this, that means you have access to it already. Very much. If you do have any question that you think you cannot really share in the group and you want to ask directly to me, you can contact me in anwar.sutan@i-Vigilant.com, or you can visit my website at www.i-vigilant.co.uk. Or if you want to know how to buy the software of GCAS, and if you want to know about more information of what GCAS can do, you can also contact jennifer.raybone@swintontechnology.com, or you can visit Swinton's website at www.swintontechnology.com. And that's pretty much my surgery on the GC uncertainty. Thank you.